For our third example of exponential growth and decay problems, we're going to be solving for k, which we haven't done yet. Let's read this question together. It says the population of a city P grows at a rate given by dP dt is equal to Kp. Now this is the same formula we use to derive our population growth equation, or exponential growth and decay equation. And again, notice that Kp represents a directly proportional. So the rate in which the population is increasing is directly proportional to the current population. Where t is measured in years, just like we talked about before, when we're talking about compound interest, we typically use years. Here's the question we're asking. What is the value of k? So I'm going to circle that. If the population triples every 25 years, so a couple more keywords to underline. The population triples, and how often does it triple? It triples every 25 years. So we're solving for k given that it triples every 25 years. This is going to be an interesting question. We're going to use the formulas that we've derived already to solve it. So again, for step one, you always want to write out the formulas for exponential growth. Here is the amount formula, or the population formula. So the population at any given point in time is equal to the initial population times e to the kt. We've already done a proof for this, where k is the growth constant. And then here is our rate formula. The rate in which the population is changing, whether increasing or decreasing, is equal to the growth constant times the current population. The question is, how do we use what's given in these two formulas to solve for what we don't know? So k is in both of these formulas, so we need to figure out which formula to use. Since we're solving for k, you would think you could use either one, but the problem is we don't know the initial population. We don't know the population at any given point in time, and we certainly don't know the rate, because the rate's going to be increasing as more people populate. So what we're going to do is go back and look and see what they gave us. Again, it says that the population triples every 25 years. This is all we need to know, actually, is this bottom line in order to solve this problem. So let's go ahead and write out what we know. First part is the easiest. We know that t is equal to 25. So let's go ahead and write that out for the first thing that we know. The second part takes a little insight, but take note that if the population triples every 25 years, then we can write the following. P is equal to 3 times the initial population. In other words, after 25 years, if the initial population was, say, 1,000, then the new population would be 3,000. We would triple that, or multiply it by 3. So again, that takes a little bit of insight, and the reason we're going to be doing that is because we can now replace the p of t in this equation with 3 times p naught. We're eliminating a variable, and now we just have the k and the t variable. Well, we already know t is 25, so now we can solve for k. All right, and I could just write this as p of t, which I guess I will do, but it's the same thing. Okay, it just means the population with respect to time. So let's go ahead and rewrite the formula and replace p of t with 3 times the initial population. So p of t is going to be replaced with 3 times p naught, since it triples. P naught we do not know, but that's okay. You can see that there's a p naught on the left and the p initial population on the right, so they're going to cancel each other out, times e to the kt. Now we don't know k, but we just said that t was 25 because it tripled after 25 years. So again, we know that the new population is 3 times the initial population, and now we have that. So that's it for step 3. We've plugged it into the formula. After we've done step 2, which is write out what we know, now that we've plugged our stuff into the formula, now we can solve. So step 4 is to solve for the unknown. Again, we're trying to solve for k because the question asks what is the value of k if the population triples every 25 years. It's an amazing problem, really, because we never even knew the initial population, and we didn't need to. So the first thing we're going to do is cross out the initial population, since they're there on both sides. So now we have 3 is equal to e to the... Now I'm going to basically take that 25 and move it in front of the k because I can. So it's e to the 25k. And from here on out, I'm just going to keep working on a new screen. So the next thing you have to realize is in order to get e by itself, you have to take the natural log of both sides. So I'm going to be taking the natural log of the left, the natural log of 3, and I'm going to be taking the natural log of the right. So natural log of e to the 25k. So again, you do that because that will cancel the e on the right. I need to put the right side in parentheses. Okay. So now that we've taken the natural log on the right, that e is going to cancel, and I'm going to be left with just 25k. And on the left, it's pretty easy, right? It's still just the natural log of 3. Not a problem whatsoever. The final step for getting k by itself is to divide both sides by 25, which is exactly what I'm going to do. Okay, once we divide both sides by 25, the 25s will cancel, and we're left with k is equal to the natural log of 3 over 25. Now we have k is equal to the natural log of 3 over 25, which is our growth constant. Let's see what that is as a decimal. Now, as a decimal, that k is approximately equal to 0.0439. Now, why is this important? Why solve for k? Well, basically what you could do with that is you could plug that back in to your population formula, and now that you know the growth constant, all you would need is the initial population to figure out the population at a given point in time. But again, I think this is an amazing problem because we weren't given the initial population. We were only given that the population triples every 25 years, and with that particular information, we could actually find that k is equal to 0.0439. Last, we want to answer verbally. For step 5, the verbal answer is the growth constant k is approximately equal to 0.0439. Another way to think about this problem is with the rate formula. If k is approximately equal to 0.0439, suppose, for example, that the population was something like a million. If we plugged our growth constant in and multiplied by a million, we would actually get a rate of increase of the town or city of almost 44,000 people per year. So as you can see, the growth constant is very important when it relates to population growth. If you have any other questions about this example, let me know.